Okay, so we are going to be covering chapter 3 for exercise phys. Da, 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 da. Okay. This is the big one, guys. So if I'm explaining something wrong, let me know. No fucking idea if I'm doing it wrong, but I'm pretty sure I'm doing it right. Not sure. Okay, so definition of bioenergetics. Just think of it as what's the process? Like that's the name is the process. We are converting food into energy. He says it like converting foodstuffs, but it's just converting food to energy. We make ATP. If I say ATP and ADP, try not to get confused, but I will try my best to pronunciate. I just don't know how well volume is here in the library with no microphone. So lovely. Um, so we're going to go on to number 2 of chapter 3, which is what is oxidation versus reduction. So oxidation and reduction is super important when we are doing the electron transport chain, because that's when we either become like pH is either negative or positive, basically, at least for our blood acidity. So it's super important in this kind of sense to know. So oxidation, you can think of it as you're losing an electron, and I'm not sure about the hydrogen ion, but it also is in there somewhere. Um, so just think of it this way. Both oxidation and reduction are going to be the loss of a electron, or sorry, oxidation is a loss of an electron and also either a loss or a gain of hydrogen. Reduction is going to be a gain of an electron and either a gain or a loss of hydrogen. I'm not sure which one, so that's up to you guys to figure out. When this reduction or oxidation happens, a free radical is formed, which is something we'll cover later on, but just think of a free radical as being something that damages you. So one of the things for enzyme role in chemical reactions or metabolism is going to be in chapter 3. There's a huge graph that's super, super important. And I'm going to go over a couple of these. Hopefully I can get over it. 11 doesn't really explain it that well, but oxidation reduction, that's the one you need. NAD and FAD is going to be something we'll cover over really fast, but you just got to know basically it's going to be used in the electron transport chain and it's going to carry that electron and hydrogen. Let's see where we at. Okay, classification of enzymes. So this is the table that we need. Where's that? On, oh my gosh, where's the table? Nope, there it is. On slide 49. So there's 4 types of ways that we really make energy. These are all individual types of ways, but however, you can use 2 or 3 systems. For instance, we use the ATP PC cycle, right? We use it. Then we use the ATP PC system when we are trying to get energy. We use glycolysis when we're trying to get energy. Citric acid cycle or Krebs when we're trying to get energy. Electron transfer chain, same thing. All this is like energy needed. So one of the things that you're going to do to kind of make it a little bit easier for you to remember the enzymes or the stimulators or the inhibitors is going to be for the ATP PC system. PC stands for phosphocreatine. The rate limiting enzyme for the PC system is creatine kinase. So it's in the name. I'll cover the stimulators and inhibitors in just a second. So for glycolysis, there is glyco is basically sugars, right? So when you're thinking about sugars, think carbo, so carbohydrates. Glucose and glycogen are your main ones that we're going to be talking about in class. Sugar, guess what? Corn syrup, fructose, right? I don't know, fructose corn syrup. So fructo or phosphofructokinase, glyco, sugar. Hopefully you should get it. Citric acid cycle, it's in the name, Krebs or citric acid cycle. It has isocitrate. So citric, citrate. And then last but not least, the electron transport chain. Don't quote me on this. However, I remember him saying something like the ETC is in the cytoplasm or in the cytochrome. Not sure. If that doesn't work, you can also think of when you are using the ETC, you are oxidizing or reducing, which requires you to have that oxygen, that that loss or gain of electrons. So oxidase, you're oxidizing something in the ETC. Maybe that's a good way. Then we'll cover the stimulators and inhibitors as well. So something that is kind of the same on everything is you're always going to have the stimulator be ADP. So adenine diphosphate, not diphosphate. Why is that? So when we're low on ADP, meaning we're low on energy, our body is going to be like, hey, we need to kick up production of ATP, adenine triphosphate, because it's a way easier way for us to get energy. Think of like ADP as being level 2 and ATP as being level 3. It's super, it's easier to get more energy that way. So we have low ADP. Oh no, we need to get more energy. We're going to try and get ATP. Opposite side, the inhibitor is going to be a lot of ATP. Why would a lot of ATP inhibit our system? Think of it as we just laid down and we have so much energy, so much ATP. We don't really need it anymore, to be honest. So our body's gonna be like, okay, we don't need all this ATP anymore. We're just gonna inhibit it. We're gonna stop the creation of it. We don't need that much anymore. Other things to kind of know in the stimulators, or specifically glycolysis and the citric acid cycle, we'll cover a little bit more later on. However, glycolysis pH can differ. So glucose and glycogen can make either lactate or pyruvate, which is due to your blood acidity, which blood acidity is pH. So that is kind of your stimulator inhibitor. For the citric acid cycle, the NAD or NADH or FADH, I know these sounds weird, they're just outputs of the citric acid cycle. Just think of it that way. NADH, NAD, NADH are like pooped out. I'll go into it a little bit later on. But so I'm checking real quick for Instagram just to make sure this is everyone has a question. Cool. Yeah, and then we'll cover into more of this in a second. So let's go back into what are we at? Enzyme roles in chem and reaction. I'm not sure if that one is correct, but hopefully it should be. Yeah, cool. All right, so let's go straight into the system. So we're going to go through the step-by-step process of how we get ATP. Let me just make sure. Yeah, the primary roles of NAD, FAD is going to be transporting electrons into the ETC or the electron transport chain. Just think of it as it's going to do the oxidation, it's going to do that reduction, it's going to either take or give a electron, which is going to make your pH high or low. So just keep that in mind, or acidity. All right, let's go into the energy system. So we'll cover over the ATP PC system kind of real fast. You're basically going to use this as your generator for, never mind, I have no idea. But we're going to go into glycolysis because that's the easier one. And I don't remember exactly, it's on your slides, somewhere in the slides, I'll find it. But glycolysis, glyco, sugar, carbohydrates. So sugar and carbohydrate, same thing. Don't have to worry about anything else. When we're trying to do glycolysis, for some reason, I have an anaerobic in here. I don't know if that's needed, but just in case, it's anaerobic. I have no secondary sources to back me up, but so there's two things that we can use, or two sugars that we can use in glycolysis. It's going to be glucose or glycogen. Now, same thing as ADP, ATP. Think of it as this way: glucose is level 2, and glycogen is level 3. So we want higher level because it's going to give us more energy. For now, base terms. So when we are doing the glycolysis to get ATP, glucose is going to give us total of 2 ATP. When we are doing glycogen, we are going to get a total of 3 ATP. Why is that? So glycogen is stored wherever your muscle is. So let's say, for example, we are using arm, right? So I already have glycogen in my arm, meaning it doesn't have to transport from the rest of my body. That's why it gives me one extra energy. It doesn't have to be transported in. Transport takes one energy. So, and this is going to be really weird to understand. Think of it as they gained like 4 or 5 energy, and then the transport just knocked it away. That was a bad example. Just forget the last 15 seconds I said. We'll continue on. Glucose makes 2, glycogen 3. Okay, glycogen is in your muscle. It's easy, no need for transport. Glucose, blood sugar, it's in your blood. It's going to take some time to transfer over. One of the things that we did in the study group was say I want to activate this muscle. Okay, glycogen's right here. So beep, 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 beep. It's right here. You don't got to worry about it. Glucose, it has to go beep, 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 and then travel to whatever spot needs it. So it's going to take some sort of ATP to use. So from glycolysis, we are now going to go into the Krebs or citric acid cycle. Pause. We are not going to. When glucose creates the 2 ATP, at the exact same time as a byproduct, the little trash can that you see like that way, that trash can, that is a byproduct. Okay, so it's not necessarily trash because we can turn this back into energy. However, glucose makes 2-lactate or, and I mean or, 2-pyruvate. This can be converted later back on into energy. However, we're going to be using it in chapter 4, so just forget about it for now. So what am I going on? Just remember that glucose, 2 ATP, glycogen, 3 ATP, one's in the muscle, one's not, it has to be transported in, and then glucose, 2-pyruvate, 2-lactose, or sorry, lactate, not lactose. Okay, now we're going to go into the Krebs cycle or citric acid cycle. So this is the biggest ATP kind of production that we have. Glucose going through the ATP cycle itself is going to